Sure. So let me just do a little bit introduce. So our last speaker today is Mikhail Vasilev from University of Glasgow. So today he will talk about generalized spin Calogero-Moser models. So Mikhail, you may just do the talk.
Yeah, thank you very much. So first of all, thank you very much to the organizers for the opportunity to give a talk on our recent paper. So I will be talking about generalized spin Calogero-Moser models. So there were several talks about spin Calogero-Moser systems previously today. So I think I will be talking about a little bit different settings. So first of all, I will be doing everything in quantum setting, and there is somewhat generalized, for which I will account later. So this is based on our recent paper, which has just appeared on the archive. So this is a joint work with Professor Misha Fagin from the University of Glasgow and from Martin Vrabets, who is now a postdoc in the University of Montreal. So the plan for the talk is the following. So first of all, I will recall just the basics on how to construct Calogero-Moser systems from Dunkel operators. So secondly, I will discuss how generalized Calogero-Moser systems could be obtained from reducible representations of the Cherednik algebra. Third will be about generalized spin Calogero-Moser systems. Then we will look at some examples, and then there will be outlook. So let's start with something sort of very basic, motivation. So here are four different types of systems. So first of all is just quantum scalar Calogero-Moser system, a rational one. So what do we have here? So we have some differential operator, which consists of Laplace operator, which classically is just sum of squares of momenta, and we have some potential. So what are the ingredients for the potential? So we fix some root system of complex simple Lie algebra, and we construct potential, which is 1 over x squared, if we sort of make things very, very simple. So alphas are just roots, and C alphas are called multiplicities. They are some complex numbers. So what we want from multiplicities is that they must be W invariant. So they are invariant with respect to the action of Weil group. So apart from, so then we have spin case. Yep.
Oh, I think there's just some like a sound rebouncing from
Okay.
another guy. So
Okay. Okay. I thought this is the question. It's fine.
okay.
So second case is spin case. So what we do, we just change this operator slightly. We introduce P alpha here. So P alpha here is a matrix, which is a representation of the Weil group. So P alpha is just a representation of the Weil group, and this is a matrix valued differential operator acting on functions of x with values in some representation of Weil group. So then there are many, many ways how we can sort of try to generalize these operators. So we can try to do trigonometric and elliptic versions, so changing the nature of the potential. Other way is to sort of go relativistic to consider Royston-Schneider models. So, but I would like to talk about another way to try to generalize these operators is to try to consider, instead of a root system, we can try to ask what would happen if we take just some finite collection of vectors in some vector space. So for now, A here is some finite collection of vectors in a vector space, is not a root system, well, something. Of course, we cannot expect that this system will be integrable. Well, these systems are integrable. But if we just take any collection of vectors in some vector space, of course, this operator will not be integrable, but in some cases, it will be integrable. And so here, all the ingredients are the same, apart from, well, we take something that can be not a root system. So, and spin version is sort of the same. So we take P alpha here, where P alpha will be some matrix. So here I can't speak about some representation of while group because we will not have a while group, strictly speaking. And these formulas are actually a little bit incorrect, but I decided to keep them shorter and simpler to understand rather than correct. So there will be a slight change to coefficients here. It will not be c squared alpha, strictly speaking, but something like c squared alpha. So, and one of the examples, so yes, I need to say that the operators of this type were considered by Charlie Goncharenko and Vasilev in 1999 with connections to de-integrability. So our aim was to sort of derive them, generalize them, and understand how they appear from the point of view of Cherednik algebra. So one of the examples of collection of vectors which is not a root system, but which works and provides some framework for integrability is the following example. So here we take sort of A-type root system, but there is some weird parameter here, square root of k. So then I need to talk about sort of the main object which will help us to construct such operators, which is rational Cherednik algebra. So rational Cherednik algebra is an algebra which is generated by while group. So we fix some while group, we fix a root system. We take dual Cartan Cartan. So this algebra is generated by these letters. So additionally, we have this multiplicity parameters, which is a map from the set of roots to complex numbers. So we only ask that this multiplicity parameters are W invariant. So which means that they are constant on the set of roots with the same length. So W, they just generate while group, nothing serious. So X's, they commute, nubbles, they commute, and we have this sort of equivariant action on X's and on nubbles. And there is one sort of complicated relation, which is, well, just some formula. So this is sort of a formal algebraic definition of a rational Cherednik algebra. So if you're not satisfied by this definition, then I can give another definition. So second definition is via faithful representation of this algebra. So instead of thinking about generators and relations, we can just think about this algebra as in some faithful representation. So what is this faithful representation? It is known as Cherednik polynomial representation. So what do we do? So we take our axes, which were from dual Cartan. We take functions on dual Cartan, we take polynomials. Then we say that, okay, let X act by multiplication, we can do that. So elements of while group, so how do they act on the polynomials? So, well, they just permute variables. And nubbles, they act by Dunkel operators, which are just these objects. So, and this is a faithful representation. So if you don't like generators and some weird relations, you can just think about these objects acting on some polynomials. And this is, well, at least for me, way more understandable than just some generators and relations. And additionally, if we don't like some root systems, something a little bit abstract, we can just take A-type. So while group will be a symmetric group. We have n variables X, and we have explicit formulas for the Dunkel operators. So, and in this case, we'll just have one multiplicity parameter. So then how we can construct Calogero-Moser systems from Dunkel operators? So we do the following. So let's take some W invariant polynomial of Dunkel operators. So for example, in A-type, this will be something like Newton sums. In case of general while group, well, there will be other W invariants, but there are enough of them. So And what can we say? We can say that invariant polynomials of Dunkel operators, when acting on W invariant polynomials of X, so this space is preserved. And this is the most important thing that we need to construct Calogero-Moser systems from Dunkel operators. So what do? We then take sort of a variant of Newton sums. So we take some orthonormal coordinates in Cartan. So we take Nabla squared, sum of Nabla squared, and we take restriction. So which means that we restrict. So this will be some differential operator of the second order, and we restrict our action. Yes, sorry. So this will be a differential, a second order differential operator, including S alphas which permute variables X. But if we restrict to the action on symmetric polynomials, then these permutations will vanish and we'll get the operator of the following type. So where this is just a Laplace operator, and this is a term of this form. So, and then we can conjugate by a formal function, which looks like Vandermonde function, and we will obtain the operator which was on the first slide. So, and then we can take, so we obtain just one operator. How we can argue about integrability? So we can just say that, okay, we have higher order W invariant polynomials of Dunkel operators. We can take them. They will still preserve symmetric polynomials. So we can restrict our action to the space of symmetric polynomials. We'll obtain some other operators, but other operators will commute among themselves. And with this operator, just because Dunkel operators commute among themselves. So commutativity comes for free as soon as we know that Dunkel operators commute. So how to construct spin versions? So spin versions are constructed in the following manner. So we take polynomial representation and we tensor it with some W module. And we say that, okay, let's say that rational Cherednik algebra will act on this module simply as acting on the polynomial part. So this V, the action on V by Cherednik algebra is trivial, but we think of V as a W module. So then we can say that invariant polynomials of Dunkel operators act on diagonal invariants in this space. So diagonal invariants mean that we can act by elements of Weil group on the polynomial part. And since V is a W module, we can act on invariants. We can act by elements of Weil group on elements from V. And if we act by elements W tensor W, so this invariance, these are elements which are preserved by this action. And then, so we can restrict this sum of squares of Nablas. Sorry, this should have been Nablas squared. Sorry. So if we restrict to the space of diagonal invariants, then we obtain, apart from scalar part, in Calogero-Moser system, we obtain also a spin part, where P alpha are operators acting on this sort of vector part W module. So this is the way how to construct spin versions of Calogero-Moser system. So how to construct generalized Calogero-Moser systems. So yeah, so sorry. So firstly, let's just look at the example. So yeah, so this is just a scalar part. This is an example of sort of A-type deformed root system. So we have two types of variables. We have x's, we have y's, and with between x's and y's, everything is okay. But here we have some again, this weird square root of k appearing, which is sort of deforming A-type root system. So the idea how to obtain this type of operators is to study reducible representations of rational Cherednik algebra. So the idea goes back to works of Dankel, Du, Obdam, who studied sort of when Cherednik algebra has some sorry, I think their work was about Dankel credits, but okay, let's keep it because I don't have a lot of time. So what do we do? So we fix the following data. So we take root system, a while group. So we draw a Dynkin diagram and we draw some subgraph in Dynkin diagram. So we denote by gamma naught V, so the set of roots corresponding to our subgraph, and we fix some multiplicity parameter. So, and to this data, we want to assign some submodule in the polynomial representation, if possible, of course. So here is the picture, for example, we take A8 and we take a subgraph A2 cross A2. So invariant parabolic ideals was studied by Misha Fagin, who proved a theorem about when these objects are really invariant under the action of Cherednik algebra. So what do? We take the plane, defined to be orthogonal to all the roots in this subgraph. So then we rotate it with the while group, we take the union, and we obtain some union of planes. And we take the ideal of all the polynomials vanishing on this union of planes. So this is the definition of invariant parabolic ideal. So, and the theorem says that this ideal is invariant under the action of the whole Cherednik algebra if and only if the following equation holds. So I'm not really sure if there is a way how to understand this equality very fast. Well, what I can say is that if all the multiplicity parameters are equal, then this relation says that multiplicity parameter should be 1 over Coxeter number for each connected part of the subgraph in the Dynkin diagram. So then how to construct generalized Calogero-Moser system? So we take this invariant parabolic ideal. So we insist that it is really invariant under the action of the whole Cherednik algebra. So it is a submodule, and then we construct a factor module, which sort of geometrically is just the space of functions on this union of planes. Then we compute sum of squares of Dankel operators, and then we want to act sort of in local coordinates on functions on this union of planes. So there are some technicalities, well, just some simple technicalities how to do that, so we'll skip it, but the resulting operator is that so what we obtain? We obtain Laplace operator on plane pi, and we obtain this sort of potential part. So y are coordinates on plane pi, and alpha hats are orthogonal projections of roots onto the plane pi. So we take root system, and where root system lives, we have some plane pi, and then we project all the roots orthogonally. So this is the way how we obtain this finite collection of vectors which are not root systems. So how to do spin generalized Calogero-Moser systems? So we sort of do the same. So we follow the same line. So we take invariant parabolic ideal. We take a while group module V. And now, so what we did, we took polynomial representations and we factored by this invariant parabolic ideal to obtain a representation of rational Cherednik algebra. So these are the functions on the union of planes. We enlarge it with module of the while group. And so this altogether is a module for rational Cherednik algebra where we insist that rational-shaped unique algebra acts trivially here and all the action is here. So, and then we want to act by polynomials, symmetric polynomials of Dunkel operators on this space and by this action to obtain explicit formulas for generalized spin Calogero-Moser operators. So what do we do? So we take W invariant combination of Dunkel operators and we act on diagonal invariance on this space. So again, by diagonal invariance, I just mean that elements of while group can act here on the polynomial part, and they can act here on the vector part, and we insist that invariant. So we act on the invariants which are invariant with respect to this diagonal action. So and then the theorem set, and the theorem we proved is that so if we assume that this D gamma node, which is union of planes, defines an invariant parabolic ideal, then there is sort of generalized restriction procedure which says how to compute. There should be derivative here. So the resulting formula is that we obtain Laplace operator on plane pi, we obtain scalar part, and we obtain some polynomial. We obtain a spin part. So important thing is to say that this operator can only act on sort of vectors which are invariant with respect to the parabolic subgroup of the while group, where parabolic subgroup is constructed is connected to the subgraph in the Dynkin diagram. So this is a parabolic subgroup generated by the roots which are chosen in the subgraphs. So if we go to the potential gauge, so we conjugate this operator by some formal function of van der Monde type, and we obtain operator of this form. So here the form is sort of simple. It's very, very similar to what we saw on the first slide. So here is the plus operator on the plane pi. So here is potential of type 1 over y squared. So sum goes over roots which are projected onto the plane pi. So this collection of vectors is no longer, well, almost always not a root system. So here is something like C alpha hat squared, where C alpha hat is sum over C alphas over all alphas which project to a given alpha hat. Well, this is almost C alpha hat squared. And this is the spin part, where P alpha hat is defined by awful formula. So integrability comes from the fact that we have additional invariants, additional W invariant polynomials of Dunkel operators. So now let's say a few words about case of reflection representation. So every while group has a reflection representation when it just acts by reflections on the roots. So in this case, so let's just put it simply. So this P alpha hats operators from here. So what we did, so we took root system, plane pi, we projected our root system onto the plane pi, and then if V was a reflection representation, then the claim is that P alpha hats, first of all, they preserve the plane pi, and they really act as a reflection with respect to the projected root alpha hat. So in the case of reflection representation, P alpha hat is really something like a representation of the while group. So this is a reflection with respect to the root alpha hat. But for more general representations, this is just an operator defined by some formula. We do not know if it has any very good meaning. So we can just define it, and we can get some commuting operators from double invariant polynomials of Dunkel operators. So yeah, so and by this construction, then we obtain operators considered by Chalog, Boncharenko, and Vasilev, who considered these generalized spin Calogero-Moser operators only in the sort of reflection representation. So, well, I don't have a lot of time, but let's just quickly have a look at A-type construction. So we take the Dinkin diagram of A-type. We take subgraphs AK minus 1, and here all of them, all the others are also AK minus 1. This is necessary for the invariant parabolic ideal to exist. And so in this case, multiplicity parameter just should be 1 over K, so that our invariant parabolic ideal is really invariant under the action of the rational Cherednik algebra. And the resulting operator is of the following type. So we have sort of two types of particles. We have n particles here, m particles here, and between them there is some deformation parameter which sort of deforms A-type root system, and these are the spin operators, which in case of reflection representations really become reflections with respect to these projected roots. So quick summary is that, so we took polynomial representation for rational Cherednik algebra, considered invariant parabolic ideal, took the factor. So we added vector part, computed the integrals acting on the space of diagonal invariants, and we obtained operators of the form like Calogero-Moser systems, where finite collection of vectors is now a set of roots being projected to the plane pi, which defines invariant parabolic ideal. So I must say that it also works in the trigonometric case. It is in the paper. So in type A, there are additional integrals from Yangian and Drinfeld factor. So, and one can also add harmonic potential in the rational case for type A, B, C, and D. So, and what can, how we can, sort of what we can also do. So, firstly, one can sort of try to obtain Hamiltonians with the opposite sign of the spin operator. We do not know how to do this. I didn't have time to say why it may be important. So we can try to generalize to elliptic systems, and we can try to go relativistic to consider Reuschner-Schneider model, rational and trigonometric. Yeah, so, and here I will stop. I'm out of time. Sorry about this.
Okay, no worries. Okay, let's thanks Mikhail for his wonderful talk. So any